First, for one thing, I'm sorry. I forgot to change tentative title, which has no information inside, for something more informative, which I will do now in the spirit of Don Zagier. Extremely nice suggestion of his title on cue. Gromov had his title and I had my title immediately, but I forgot to change this. And to be even more short, we may put just n going to infinity and nothing more necessary for this title. So title should be correspondingly adjusted. Okay. So, of course, geometric analysis is a name which used so often for very different things. So you don't read, I will read. But it comes formulas. Okay? And in fact, and I should explain what I mean, what will be a real subject. It's very often used completely mechanical, just to use analysis in geometry or vice versa. And I mean completely different thing and some kind of ideological influence, mostly of point of view of analysis, or better to say functional analysis, which change questioning which we ask in geometry, and it is what we will see. And this happens mainly through isomorphic study of geometric object. Before I describe the subject, again, historical point only, small, I would like to say that it was born inside functional analysis. And in fact, during all of the 20th century, a lot of different directions were born and germinated from functional analysis. And this topic only the last of them. And this gives to him justification to be presented at this meeting as the last of them. Also, it's so recent that I don't need to talk about future. The subject is future. If one is to ask what's the subject of functional analysis at the same time, I think it may be said very shortly and correctly, dimension equals infinity. So we have two classical theories. One theory is about finite dimensional situation, which I call small dimension. And small is any but fixed number. It was discussed in Peter Jones' talk, large dimension. But for me, it's small, because all his constants were dependent on dimension. So it was, in fact, in fixed dimension story. And another is, in fact, infinite dimensional, which is functional analysis. However, there is a third possibility, a theory in between, the study of finite dimensional spaces with clear emphasis on asymptotic behavior. And my first goal is to show that such theory indeed exists. But I will not do just this or that result, but I would like to demonstrate the new intuition which comes with the theory, and new structure is developed. To do this, I will just present some small collection of results, but I choose them in a way that it's avoid any, it's elementary. It's avoid completely new terminology, which one need perhaps some time to learn before to understand of result. However, unfortunately or not unfortunately, I don't know, no result has elementary proof of what I present, but formulation would be completely elementary. It is more difficult to do with structures. Structures involve some terminology and more involved usually technique. So I will present only one of such structure in the second part of the talk, and it is very powerful tool which we call concentration phenomenon, and which used through all of the theory. And my choice of this subject has two reasons. One reason is I believe it is the right tool, not only in geometric analysis, but in all problems which involve deal with large parametric families, complexity theory, asymptotic combinatorics, I would call this, statistical physics, and so on. And it's already intensively used in some of these directions. But secondly, we will see that it is a typical example in the spirit of the theory I want to present and the consequence of an isomorphic view on classical geometric problems, more precisely as a perimetric type problems. So a change of point of view, a change of concept made possible discovery of new phenomenon, and this is perhaps some kind of message which I like to tell. Now, as Jean Bourgain said, it's very difficult sometimes to put precise references and talk on the result you want to put. In my case, it is because they extremely interlapped in different collection of after doing this, sometimes it's far-reaching interpretation. But I will not do as Jean, just ignore people. I will just put the list ahead of time and will not remember this anymore. And again, I would like to say that it's not a group of people who exactly fully developed the theory. For example, there is no name of Gilles Pizier, who greatly contributed to the theory, but I just did not select his result. In the collection I will talk, it's the only reason. In the second part, it would be another collection of names, and again, it would be about concentration phenomenon, and again, it would be not name of Talleyrand or recent star in that direction, Babkov, just because I did not select this result for discussions. It's the only reason. Okay, we start mathematics, and very few obvious notation. So Rn is Euclidean space, and this absolute value sign is just Euclidean norm. It would be more for this. And n I view as parameter, which would be tending to infinity. C is constant, but it's absolute number. 3 or 10, we most probably don't know these numbers, but they don't depend on anything at all. Now, K is convex compact. I consider this to be symmetric only for simplicity. All results are true for any convex set, but just then I should choose position of 0, which I don't want to be distracted. D is the unit of Euclidean ball. Also absolute value will be volume of set, and equivalence is equivalence as it's written, and sometimes I don't write C, but it means that it exists, universal C. And perhaps the only number which not everyone may heard, but I believe almost, is covering number of set K by T, and it is a minimal number of shift of body T which cover body K. And sum is Minkowski sum, meaning all combination of X plus Y from these two sets. So you see, not too much we will need. Okay.
More than 7 things.
But you knew all of them. But what? I will use when it will be necessary, not for this. Starting result, I will. Okay, I will put this, but when result started, I assume to do this. Okay. And now we will start with first result, which again, purpose of result to show intuition and some principles which will develop from them. And perhaps I will close. I hate to close things because we live secret times, yes? But I just don't want to be distracted, that you will be distracted by this. So, result, theorem. What I do? I want this to see. Okay. Theorem. So you see in brackets I put there exists C such that for all n. I put this in brackets because it will be an all result. So there exists universal number C such that in any dimension for any set we may find ellipsoid, a linear image of D, such that now for any other T, if we need to compute volume K plus T, we in fact don't need this set K. We may substitute this by this ellipsoid. In the rough scale up to constant C. The same if you study intersection and want to know volume, we again don't need K. We in fact don't need K. We need only ellipsoid. Up to the same constant C, it would be the same computation. If you need to study covering number of K by T, you see this is volume, it is more such integral parameter, but now it's much more geometric, it's covering. We don't need K, it is enough to put ellipsoid, and we will have the same number. and again in opposite direction. In fact, most of this result following from fact which I will put now, but I think this is more show what I want to say, and we will open and we'll see this principle. In fact, covering k by epsilon and this ellipsoid and ellipsoid by k, all of them, this number always more equal 1, so I just say that both of them is of exponential order. Okay? First, before we come to this, let me note just that, of course, you cannot expect better than what is written. You see, you took power 1 over n, so one may say it's constant to power n, it's too large difference. But you cannot expect, because even if you will have Euclidean ball and twice Euclidean ball, or say ellipsoid, if you like to have the same volume, here dimension n over 2, and say twice large, and here only half. To have covering by Euclidean ball, you already need some constant to power n step. It is covering in n dimension. But generally, arbitrary k may be far, like say cube, or from ellipsoid to the root of n. And so, and for not symmetric set, it like simplex and Euclidean ball, distance even n. And so expected number a priori is for C something like root of n. So you expect root of n in the upper numbers, and you would expect correspondingly logarithm here. But instead of this, you have universal constant. So, so from the point of view of this volume covering geometry, any k looks like an ellipsoid. So now I would like to read principle which you know, I put one example, we may put much more, and I will continue a little bit, so I will not have time to do more than one example on every principle I want to say. But principle is that, in fact, just find this family, group GLN, is rich enough to represent any convex body in all volume or covering computation. So, and in fact, this ellipsoids family has nothing specific inside. I could start with any body P and consider and say cube for analytical number theory may be much more interesting. And then consider such images, linear images of cube, and this would be enough in the same way as I discussed this ellipsoid. So, point which we see is that in fact, there is not so much diversity as one could think or expect in very high dimension, but only when we took point of view of isomorphic to do things up to universal constant. And now, just, okay? Okay. So on next step, I would like to go more to geometry. Before we discussing a little bit on some kind of integral level, yes? But in fact, in a very pure geometric sense, the same fact is true, which is even more perhaps surprising. And I just put it here. So, result is written here is the following. For any k, now I normalized volume to be the same as volume of Euclidean ball. It's just normalization for constant because this volume radius equal 1. One may choose a linear image. It is, later I will do this on next slide, I remember even without this. It is just to having the answer not ellipsoid, but Euclidean ball. Such that there exists two orthogonal rotation. And if you intersect that k bar, this position as we call of k, with rotated, so you a little bit cut off, but it's n dimension, it's only one rotation. And then you take sum, or convex hull, you take it the same for this situation, of this body P with another rotation, what you receive is in fact Euclidean ball. There is not much distinguished parameters, they're very little. You cut them by one step, and you, by adding, you fill everything which is extra. And
volume-wise, what?
What?
What's the equivalence means?
This? No. Up to this is written what equivalence means. Okay? By the way, we call this distance. In fact, in formal definition, c times c squared would be distance, geometric multiplicative distance of one body to another, that you would not ask me later question when I put distance. It is put here. This is product of these two parameters. Yes, but of course it also means that volume did not change much, but it is that in both operations it did not change much, but it's consequence of what is written. Just for a minute, of course, this is, I like to say, and I will return to this, I will try to call Q to be ellipsoid in isomorphic sense. We will discuss this in a minute. But in fact, even perhaps more geometric fact may be put, such epsilon version, that if instead of V you will take some numbers written here up from 1 to c over epsilon squared, then in fact, by rotating, you may indeed approximate up to epsilon ellipsoid. What I want to observe here is that it is dimensional free estimate. So dimension going to infinity, but number of rotations stays the same, which you need. Okay? So let us continue. I still will accumulate interpretation. Oh, just a moment. One only remark. In fact, I say exists, but we know to prove large measure. Is it more? No, it's less, because we don't know to present even one V, W and V for any reasonably not Euclidean body. This is another problem which I will mention again, but which stay for us, and for some formulation in the end, I'm ready to put price. And I will put just much easy formulation. This is much more difficult, but for some very easy things, looks. And I pay my prices. Bizet receive once, and Jean receive once, and perhaps also Talaga.
Put it up.
Huh? Don't worry. I will come to this. It's in the spirit you know, yes, so perhaps. No, it is not true in infinite dimensional. I just decided that I talk geometric analysis and not functional analysis. As a result, yes, I don't discuss this part, but there is this huge and principal difference in the theory of the asymptotic finite dimensional and infinite dimensional. There exists completely different phenomenon in two theories. Some of them discover Gauss, some of them Adelian Schlumpretz in this level, but there is this gap, there is this jump, there is this different completely effect. This is dimensional free and not infinite dimensional. Yes?
Is this statement not trivial for the cube?
Not, absolutely.
Huh?
Absolutely. Not
Absolutely
non-trivial. Now, by the way, for cube, let me tell you what's necessary. For cube, you don't need to take this step, take this out. If you take sum by one, it is already became Euclidean, and this particular case is Cashin. It is the reason why I put his name very long ago. It was some, so.
It's a non-trivial result for the cube.
Not true. And for cube, for example, it's easy problem, but please, I would pay for this problem, but I do this better than money. Who interested? I do picture from my collection, so it's something more valuable. Yes, for cube to find this 1V, yes, which will do the job and create a place, we don't know this at all.
How to find this V? Yeah?
How to find V for cube? P is cube here, because we don't need this step. So P is cube, you take sum, how you create this? We don't understand. Yes, if you will take dual to cube, what called cross polytope, L1 ball, yes, then this step is enough. We don't know this again. No, but I said we don't know, and this is, yeah, just for intuition. Okay. Okay, so our next step will be, in fact, I repeat now formulation of theorems, but there is this reason, one reason why I do this. In the upper, it stays the same theorem I put already. You see, I did not turn Kane, so result is ellipsoid and not Euclidean ball. But I would like to put this in functional analysis interpretation. First, let us read this, and then I say why I put this. So theorem in functional language would be that for any norm, no matter what dimension, but finite, there is this three linear operator. It could be two, but I again want to come to some specific Euclidean norm, such that if you create new norm by adding two rotated norm, and then you take infimum convolution, which I describe here, norm you receive would be uniformly equivalent to Euclidean. I say this because, in fact, this theorem is proved. All this result, which I present as geometry, is functional analysis. All technique and proof are functional analysis. But, and it's funny, and all geometric result, I said before, is interpretation of this theorem. But we switch. I like to talk about geometry and just this. And in this language, one thing is natural. I don't need to explain when I say Euclidean, isomorphic to Euclidean norm, uniformly, it's obvious. When I say that body I received before is isomorphic ellipsoid, is question what it is. Yes, because, for example, when I want to put just a definition which imply, I don't think that this is okay to be consistent. Yes, and such terminology asymptotic. So, in fact, you see, I like to think about this object, even that we discuss this as fixed object in one dimension as family. And then whatever is the result of previous theorem is in fact isomorphic ellipsoid because there exists C, common number, common bound. And for every of them there exists this ellipsoid. Perhaps I should again have some note here to have again better thing intuition. Let's see, we'll be safe. We don't know these numbers. But assume it's number 3. What it means? It means that, for example, this square is isomorphic ellipsoid, but it's part of the family, because here distance is only root of 2. And Q would be also maybe, it is part of my family of. And this would go up to dimension 9. In dimension 9, it is still root of 9, 3, and it is cube, is still belong to family. But when dimension increase, then body should change. And then, in fact, for large dimension, when normally a body already has very big distance to Euclidean, when you stay on the same C, demonstrate to you, in fact, that you deal with isomorphic ellipsoid. Geometrically, this is some kind of thing which is necessary to accept, but on the language of functional analysis, it's completely obvious. It is what we call without much thinking. So, okay. Now we will go to more result of such asymptotic theory. And I will put the following slides. Okay, let us see all this. So first, now I will talk about phase transition and threshold. So, in fact, I choose this because naturally, this theory has a lot of common with statistical physics and asymptotic combinatorics, where these notions appear. And in fact, every such study of very high dimensional space has the same phenomenon behind. And I would like to demonstrate this phenomenon in this theory. And then perhaps we will have something interesting also on this interaction. So result here is the following. First, now any bounded set, not necessarily convex. It's the same, but just why not to say, when to introduce structure which we don't need. Then two parameters I need to introduce, diameter, which is obvious, and another one, which is mean width, so-called. And it defines in the following way. If you have direction x, you just width, it is just this distance between two hyperplane perpendicular, yes? And then you just integrate this by Euclidean sphere, probability normalized measure, and it is what called mean width of the body. And then question we ask is the following. Consider projection, orthogonal projection of this set on some subspace dimension M. Take diameter of what you receive and expectation. I will put all formula, and this I call dm. I will put formula for expectation, but of course it is exponentially huge measure of this subspace into which the same is true. You don't need to take
And who is chi and who is r? You project to which dimension?
I project on dimension E. It is P is orthogonal projection.
Which dimension space project?
M.
M is projection, dimension of the image.
Yes, it is N is original dimension, and you project on dimension M. And then fact is, there exists critical A. There is no...
No, there are small ones.
What?
It's rank. It's rank.
Rank equal N. Okay, dimension rank.
What's Arnold times K?
Right. Wait. Go to the statement and we work our way back.
Yes, but so there is this critical number. For any m above this critical number, this decay as root of m over n dA. This is universal constant mean. So this is exact decay, this is line, up to constant, this is fuzzy region, because this is up to constant. But no matter what is A, no matter what is dimension, this is a curve of decay. Always the same, uniformly by all set. Then happened to be critical number, and a critical number is stabilized and became m star, the same mean width. So this is stabilization. So we see clearly phase transition at point k star, but in some kind of fuzzy form, because there exists universal constant involved. In fact, there exists additional information. The only reason why projection cannot decay anymore is that it became a Euclidean ball. But not Euclidean, this may be discrete set, so it became a net inside the Euclidean ball. I put this in strange form because formal definition of net, set may go far out of set. So I wanted to say that first it's inside and second it is net inside. So because of this is strange form. So the only reason for set not to be able to decay in absolutely regular form that projection became Euclidean set or around Euclidean set. Okay.
K star depend on?
What?
It's instead of...
What do you ask?
What does K star depend on?
It's a written formula. This is critical value. N dimension time m star over d. This over this. Okay? We will return perhaps later to something of this, but let me put this now here.
So what's,
Yes?
what is varying? There are no quantifiers.
What?
For all A.
What?
No, but K star depends on A.
What? Don't, I don't, ask me a question. Why everyone?
What is varying and what is fixed?
No. So first you take A in any dimension, you fix this, you consider projection, and you average, you take expectation by all projections. Random. So it is the same to take random with high probability subspace and project. You ask question, what is diameter? Answer is diameter is this, if m is above k star.
What's tilde?
Tilde is, as I explained before, is universal constant, which I said this when I put. So theorem should be read then, there exists constant C, such that whatever is written. Yes, it I said in the start. This is a theory.
No, I wrote down everything you said.
No, so I return back. So that this d whatever dm divided on d stay between c times root of m over n and below 1 over c times root of m over n. And this is universal constant independent on anything. In first theorem, I put this in brackets and said this would be in all theory, in all results theory. Okay? So, I will put the same fact in different form. We call this global form. It is a remainder of functional analysis inside, because when we discuss subspaces or projection, thing connected with linear structure, we call this local result. And we discuss fact which is true in the whole space, we call this global result. So I call this in global form. And in global form, result would be the following. It is not the same proof. It's different fact, but they always connected. This is mostly experience than theorem. That now I will consider orthogonal rotations of this set. And I will add this in Minkowski sum and average. But now I will introduce slightly different parameter. Minimum, the best diameter you may achieve by different rotation. This would be d bar. What? Minimum of UI, and I did not put in notation UI. It's of course depend on UI, just not to put this. Minimum by all UI. Then first fact, again there is this critical value. Before this critical value, and still for everything, independent on critical value, the best minimum proportional in the same up to universal constant to expectation. Random and the best are the same. This is property of global result, but in some sense. Okay, and the formula is that the decay going by formula 1 over root of t dA, again it is absolute constant, again independent on dimension set of anything, but only up to critical value, which is written here. By the way, this value never pass n, because d over m star never more than root of n, and this is by itself interesting that we will compare this.
Yeah, if it is a ball, it doesn't decay.
What?
Apply it to a ball, it doesn't decay.
If it is ball, because this critical value will be equal correspondingly 1. So you just don't do anything. You don't need to do anything. So again at CA we have phase transition. And again the only reason for the fact that it cannot decay is that you everything to be Euclidean ball. There is no other reason. Okay? And it is by itself interesting to return to this, that very few rotations, and not more than n in the worst case, needed to achieve Euclidean ball from whatever set you started. It's n dimension, and it is the only thing which we need. We will need some of them. Okay. Now I would like to have 2 comments on this fact before we continue. And my one comment connected with threshold view on the result. You see, returning still to what I wrote here, in fact, the interest of geometry is not the study of this diameter. We will return back to analogous question in statistical physics, where this is a question. For us, it is interesting to see when this sum became Euclidean ball, this number, when it became Euclidean ball. This is what is interesting. And so we could study, instead of diameter, directly this parameter, how far you are from Euclidean ball. And we see that it is wrong a little bit parameter. Because example I want to take first. It is just interval. Then m star is 1 over root of n, it's easy to compute, and diameter decay 1 over root of t, it is just obvious. You take the best, you constructed t-dimensional cube. But if you consider this body and consider how far it is from Euclidean, in a sense I explained when Misha Gromov asked me a question, then we see the following thing. For t below n is of course infinity. You cannot accumulate dimension n. For t equal n, the best thing is cube, so distance is root of n. It's enough to pass a little bit n, and you have fixed distance to Euclidean independently on dimension. Very sharp threshold. Okay? So if you comment, basically, in our theory we know all functions. We know this function too, but it's not now important. So you see what I want to comment. First, about this comparison, I believe that, and I know examples in our theory, that it is always phase transition point correspond to threshold in another formulation. In fact, in interesting formulation, it's threshold. And in the formulation, but we may find and locate parameter, yes, on which it depends continuously and create threshold and contain phase transition by the only reason that body became extremely symmetric. And if you study the symmetry, we see only threshold. And we don't see this continuous. Well, I think it should be interesting also to go through this and study this also in, say, combinatorics, where there exists a lot of threshold study. But I think it's interesting to see this on the language of phase transition. And another thing what I want to say, it is to know some approximation problem. I go through some sign of the theory, so I very quickly try to do this. And this approximation story is the following. What is written here is that when you take just a little bit more than n intervals, you approximate Euclidean ball. Let us see what it means. Just you see, I have Euclidean ball. I distributed in some sense these intervals. This is one interval. This rotation is all interval. Another interval. Altogether some numbers of intervals. Say n. We are in dimension n. Now, if this number n will be significantly less than e to power n, that's O small of n. Then we may find two hyperplanes on very small distance, each of other, such that all these points will be inside this slice. In a case when I took only, say, power of n, not only linear as it's here, but say some power of n, then this size would be just like 1 over root of n. So we have terrible not balance when we choose a set. And so, if you ask question, what's set intuition? How many points we need? Of course, you start at this point which you think should represent all spheres. They should be well balanced. And so you would not expect that less than exponential number of points may be regularized to become a Euclidean ball. And it was once very surprising that in fact logarithm of this number is enough. And we will see this many times. Many times we will see that in fact in approximation problems, what theory give is logarithm of expectation, what was expected before theory started. So if expectation was n to power n for number of symmetrization, which I don't want to introduce, the answer will be real n logarithm n, and so on. So we have essentially linear estimate in every problem where just looking locally on the body, we just cannot understand how this could happen.
So just for interval, can you explain why it's linear?
Oh, not. No. Indeed, I may, in this session of question, I may give you proof, I may bring you to result you know, but perhaps, but not now. Now I said, there is no trivial result between what I said, so you cannot, okay? But it may be explained, it's very short. In fact, being some period very not, how to say, not fashionable direction, we put extreme efforts to simplify proof which were originally extremely long. Say Dvoretzky theorem was 50 pages, now it's 1, and so on. But even factor all these stories, yes, it's still not trivial to show. Now, what?
The length of a proof after a theory, development theory, logarithm of original length.
But it is more, it's double logarithm in case I said and in many others. No, it is answer, Dima, for some discussion long ago we had with Misha, so this is between us, this is different story. No, he threatened me by the fact that the linear proof of, because I has 2,000 papers to read. And I was really impressed, but then computed how many pages altogether we need to prove some theorem, just as they were written, and it happens the same 2,000. So then I understood that just if you work very hard, perhaps result is better, but I don't know, this is answer of what we discussed. Okay, now I would like to see something else, but before I will go to this, I will put back one slide we already had, this slide. And I would like to consider concrete set A here, and I will take for this set now cube. And in fact, if you like, it's the same vertices of cube. What is the difference? So n-dimensional cube, so you have these vertices, and this is my set A cube, or vertices of cube, and I will consider this problem of projection. This is what my friends explained me is in fact a study of this diameter is in fact such toy model in statistical physics. When you project these vertices on some m-dimensional subspace and consider diameter, it means the largest supremum of this norm of projection, and you average this by all, take expectation, large measure, what happens? So it is exactly study of this dm. But it's study of dm for the case of cube, and for m over n to be proportional. And so I would like to see difference between two approaches. One approach, I completely forgot when I started, I can say. I even did not start. Huh?
About
5 more minutes. Then I understood all previous speakers. I don't have any pretension to them. And I know that we have a lot of time before it.
not more than that.
Okay. Okay, so, you see there is this difference in approach, so I indeed did not start. And so you see, we study things up to constant, and statistical physics want to know limit, and this is difference. Limit of dm, as I put, divided on d is root of n, if you like. And the only thing I say is that it is root of alpha, but up to some constant, not limit, but some kind of... Okay, this is very interesting difference, because for us this result is completely satisfactory. And in fact, more of this I could say. Till very recently, I almost objected. I did not support attempt to put result in more precise form with some more isometric form. And the reason was the following. Moment you go back to more isometric result, you are back to the ocean of diversity which has n-dimensional space. And then you lose picture. And if you wanted to go ahead and to see how these clusters of good behavior appear, you should keep this constant appearing. But now we are quite developed, and in fact I would be completely not object and very happy if, for example, in this problem we discuss, exact constant would be exact constant and critical bodies would be presented. We never studied this. I don't know anything about constant, any estimate, just because I saw that it is wrong question even to discuss. But now on this stage of development, this is hugely difficult problem to find extremal bodies and to find exact constant, but I think it is tiny problem. And so returning to this anyway, immediately when just very recently in the talk of Talleyrand on Bourbaki seminar, and then with help of my friend Pastor, I understood that it is our problems in a sense, I may immediately add information to this. And information would be the following. So in fact, we may go on much more delicate scale, and result is that outside zone of phase transition, we have very good approximation. So going far better and better. So if, as often happens in our problem, K star would be some power of n, less than 1 power, then on all this K we will have exact limit. And only phase transition zone is fail. Of course, in physics question, we have this phase transition zone, which is natural. So for this cube, this ratio is root of pi over 2, and so we all time in phase transition zone. But I'm not very discouraged. It is clearly to me that inside phase transition things depend on much more parameter of the body. It's not so general, and they should be more divided and more understood from this point of view. Okay.
If an individual says like you, do you know existence of the limit?
If he will give me this meanings, no, if we have discussion, I will be very happy to. I even don't have no questions. Yeah, I just want to come to second topic for a minute, and then, you may stop. So in the second topic, again, I just put name of people who whose result may be found inside what I will say, and just if you already, so I just will start very short overview of few minutes of content. I did not assume to do this long, anyway. So, but I forgot when I start indeed. Okay, so classical concentration phenomena is the following principle, is the following schema, I don't know how to call this. We consider metric probability space, and we introduce concentration function, which is classical isoperimetry. As a perimeter, we take set A, we extend this epsilon, we take measure, we see what is tail. And this tail called alpha. It's classical isoperimetric problem. But important observation is that in many examples, this alpha of x epsilon is small. And I'm sure that who never heard before this subject have completely different picture of what I want to say. Because classical approach will say what it is for, where parameter on which it is small. So it should be epsilon, small by epsilon. Then it returns us to classical geometry, and we will miss phenomena. So the point is, let us look examples. Only through examples we understand the point. So, you see, this is, I consider, typical examples. Couple, we know enormous amount now. This is a Euclidean sphere, Stiefel, orthogonal group, permutation group. This is all other thing clearly. I did not introduce a lot of things. I did not explain what distance we should consider. Forget this. This is details in a sense. So examples are xn, yn, zn. It is enough for a moment. Then the observation is, for me, all this subject of concentration phenomenon is the theory of examples. A lot of examples, and you should develop example, build approach to prove this, and so on. So I look on this as on examples. So in many of these examples, we have one of two estimates with right and very such reasonable normalization, which is usual. By the way, I will say no word without much meaning, but I ask, it is one of the, to give meaning for this. Because in this example, on this, we have this estimate. In a sense, this is elliptic example, whatever it means. In this example, we have this estimate. It's much more reasonable to call this hyperbolic example. But we see this division on two types of examples, and should be theory behind which says this. And I believe that representation theory was not enough involved, but it's again another way. It is involved to prove that this has property. We need T property of Kazhdan. But anyway, this is very much not enough. But looking at this schema, we see something. We see that, in fact, I don't think in the term of one space. I think in the term of family. But of course, what family? This n and this n, how they connected? Natural family. I did not say what I mean. But there exists some kind of natural family, and for this natural family, which we have many series of such examples, many methods which proves them, very different methods. Now, but returning back, there is this one more word. You see, when I say that it is small, now I mean, of course, sequence of spaces, sequence of these subsets. So it is not in one space. It's geometric question, but consider again in the family, and only in the family we may realize what's going on here. Serious question now.
Yeah.
It's finished, or just, no problem. To go to conclusion. To go to conclusion. No. I will not, I will try my best not to do this 10 minutes. So, you want 10 minutes, and then, okay, then I go to conclusion. Finish, no problem. I indeed lost connection with time, but I will go to conclusion remark and so. One page. So concluding remarks I would like to say. So I did not talk about concentration, which presents some of other things we wanted to discuss, but let me just say in the end that what I try to present is some kind of future of the world of very high degree of freedom. It looks very different from what was expected when we entered this world. The exponential estimate we expected in approximation procedure has happened to be linear. I had this example, and we have a lot of examples of such. In many problems, the expected diversity is essentially reduced to the orbit of group GLN. However, for this, we need to take another angle and adapt isomorphic view point of view on geometry. Quite non-trivial functions are with high probability almost constant. This is concentration phenomenon. I did not explain this. However, this is still not enough, because one may say that this small probability, when it's not constant, contain a lot of information. It is true, of course, and then it is vision. It is not vision in our sense. It is false. It is a wrong point of view. However, again, I did not talk about this. We may describe this also in geometric sense, and similar phenomenon of function to be constant in geometric sense. Every function, almost every, with some kind of small ellipsis type condition, may be also described. We know many more results of this nature, which very much contradict to early developed intuition, and I believe that much more surprising result will be in the future. And my main vision point for the future here is that, in fact, new subjects should be formed, and I believe that all asymptotic theories, being this what I presented, asymptotic combinatorics, complexity, and part of statistical physics will be very soon one subject. It is obvious, but it should happen. Okay, I'm sorry.